So now we will talk about quantization of models. So usually what happens is that the LLM models are huge, and when I say huge, they are very, very, very huge in size. Now, these models usually are in a standard size, somewhat like 7 billion parameters or 70 billion parameters for llama, you can say. Now, this large size of LLM makes it very useful, right? We are able to use it for prompting and we are able to get a lot of information out of it. We can make use of it, and these uses are endless. But the issue is that while training these models or while using these models, a large amount of space and compute is required. So even if I want to get some response from these models, then also I will have to use a lot of compute for it. I will, and sometimes it might takes 10, 15, 20 minutes to get the response. But we don't want that, right? We want the response quickly, because if you wait for ChatGPT for 15, 20 minutes, then it doesn't make sense, because sometimes you just want some responses very quick. Will you really use ChatGPT or Gemini if the response is coming back in like 5 minutes or 10 minutes or 15 minutes? You won't wait even till 1 minute, I must say, right? So same thing goes here. We don't want to wait and we don't want to put in so many resources. When we are running these models, we want to run it on a maybe a smaller GPU. Some people might want to run it on your normal laptops. So not everyone has that much resources. So we want to use them very judiciously. So what we can do is that, because while training these models, you can't hold back. You can't say that, okay, instead of training it with a 64-bit, let me train it with parameters which are holding only 4 bits. Because then your model will not perform that well. And the training will also take a lot of time, and the performance may not be that good. So we cannot hold back while training the model. Then what should we do? So what we usually do is we train a full-fledged model. Okay, your parameters are parameters which are saved in larger size, basically maybe 64 bits or 32 bits. And then you basically decrease the size of these memory which each and every parameter is taking. Okay, so instead of each and every parameter taking 64 bits or 64 bytes, you basically convert it in such a way that it actually takes maybe 4 bytes of memory. Okay, but when you decrease the size from 64 bytes to 4 bytes, the uh, this particular information will be lost. So if you see here, we have this floating point 32 data. So basically, initially my each and every parameter was floating point 32, okay, and it was taking 4 bytes of memory. While taking this 4 bytes of memory, it was capable of saving this pi value till so many fractions, 30 23 bits in fractions itself. Okay, and when we decrease the size in which this data is saved, the some amount of information is lost. So instead of being able to save 23 bits, if we use BF float 16 instead of FP32, we will be able to save only 7 bits of the fraction. So rest of the information is lost. Now instead of BF16, if you use FP16, you will be able to save a fraction bit, basically 10 bits of fraction. And if you use int 8, you will be able to save only this much. So basically you will have 7 bits of fraction saved and only one sign bit. So a lot of information will be lost. So we want to compare that. We have to decide how much information loss can we actually allow in this case. So basically we have all our parameters which have been trained to FP32, and then we just ask the model to decrease all those parameters size to a smaller size, and this smaller size is int 8 or b float 16, and this way you save memory. You save half of the memory here. Initially it was taking 4 bytes, now it takes 2 bytes. So your model being a size of say 8 GB now will take only 4 GB space. And similarly the compute will reduce. Similarly the time taken for inference will also reduce. Right? So this is what quantization is, that you decrease the size of the parameter value being saved, which will impact your accuracy slightly, but it will improve the speed, and it may also decrease the compute which is used for making inferences. This is quantization. And here we have a small chart where we have memory needed to store one value. Then this is the size. So if you see, the size is basically, here we have 32 bits, 16 bits, 16 bits, and it is taking 2 bytes of memory. So to give a standard value, you might want to go to b float 16, because in case of int 8 you will lose a lot more information comparatively. So we will play a little safe and go till b float 16 when we are performing quantization. Now let us have a look further. So when we have a full precision model is the model which has not been quantized. So in that case, if we have a 4 GB model with 32-bit full precision, then the GPU RAM needed to store 1 billion parameters would be this much. So for 1 billion parameters, this much memory will be needed. A very small amount of memory will be needed. And this is the GPU RAM needed to train larger model, to a model with 1 billion parameters. Now, if the number of parameters increase, if there are 175 billion model parameters, then this is the increase in the size of model. Basically, the increase in size of RAM needed to train this model. And instead, if you have 500 billion parameters, then it will also increase exponentially. So in this case, what will happen is that when the model size will increase, you will have to split your model into smaller GPUs to train it, but still it will need a lot of compute, and it will not be feasible if you want to train something for just maybe a trial or something. So it is better that you use a model, you basically use a quantized version, and this will actually save the RAM which is needed to train the model. So it will in case also save your different compute and the resources which you are planning, it will save money for you, right? So even in large organizations, we can't afford to lose so much money. So we will still want to have models which are maybe quantized till 16 bits, right? Because in that case, you will be using half of the resources. Okay, so that is what quantization is. Now, there are different types of quantized models. There are GGML model, GGUF model, GPTQ, and AWQ models. Now, this is the chart which you can maybe keep handy to understand what each one is used for. So let us read through this. So the first one is GGML model. GGML is basically general purpose generative model for low resource language. Okay, so this is basically low resource model for low resource languages. Why do we need it? We need it, basically it is designed for efficient training and use with low resource languages, basically where we have fewer training data examples available. So it has basically, uh, it is capable of being trained on a smaller data set, and the major use case, basically primarily it is used for tasks which involve languages with limited training data, which allows it for a better performance compared to applying large models to such languages. And the size of this model can be smaller than a full precision models, and the performance basically would probably have a lower accuracy in comparison to a high resource language model, but it is mainly made for low resource setting. So if you want to have something which is trained on a limited data set and trained on a smaller data set, less number of languages, and you don't want it to perform so many tasks, you want it to perform smaller number of tasks, then you can go with GGML. So this will not take much resources, but again the performance would be quite low. When we talk about GGUF, the GGUF is generative GPT update format. So this, in this GGUF, the format has been updated, and it is mainly used for efficient storage and loading of GPT models. And its main use case is that it speeds up the deployment of GPT models by enabling faster loading and potentially better resource utilization. So in comparison to GGML, it will have a faster deployment, and it will have a better performance. And here you can use it for both GPU and CPU. And mainly GPU is preferred for loading because GPU is faster, and it is mainly used when you want to deploy a pre-trained GPT model, right? When you want to use a pre-trained GPT model. Next is GPTQ. Now, GPTQ is basically used, it is generative pre-training transformer quantization. It is mainly used to reduce the model size and improve inference speed of GPT models. So basically, this will be used mainly on GPU because it will also improve your performance, and it is smaller in size, and it will have better speed, but there would be slight decrease in the performance. So the accuracy will basically decrease a little bit in case of GPTQ, but it will have a faster inference speed. So if you want to have a model which basically gives response very quickly, then you will go with GPTQ, because both of the other ones are quite slow in comparison to GPTQ. And while in case of AWQ, again, it is fast. Now, another thing about GPTQ is that it is significantly smaller than the original full precision model, and it offers substantial speed improvement due to the small model size, and it also has less computation resource requirement. So it may have a slight decrease in the accuracy in comparison to the full precision model, depending on the quantization level which is on it. So if you have a very low level quantization, so let's say from 32 bits you're going to 8 bits, then the speed would be very much, but the accuracy would be very low. So you will have to take care of the trade-off of speed versus accuracy. Okay, then the last one is AWQ, which is adaptive weight quantization. So in case of adaptive weight quantization, what happens is that it makes sure that it is quantizing the weights and the selecting weights which are actually needed for more for making the inferences. The more impactful parameters, not all the parameter weights would be changed. It will modify the weights which are um, more important in making the inferences. So it basically is used when we have want to dynamically adjust the quantization level of model weights during the training and the inference for optimal memory usage and speed. It basically aims to achieve a balance between accuracy, the model size, and the inference speed by dynamically adjusting the quantization based on the training data and the hardware. Now, it will be obviously smaller than the full precision model, and it will try to balance the speed and accuracy, and it mostly offers a very high speed improvement, and it will still maintain the accuracy closer to the full precision model. So in comparison to GPTQ, AWQ is quite new, so you may not have it available on Hugging Face for all the models, but in case you have AWQ, then it will obviously have better performance in comparison to GPTQ. But in case AWQ is not available, then you should go with GPTQ. Okay, so for choosing between GGML, GGUF, GPTQ, and AWQ, mainly if you want to have a low resource language, then you should go for GGML. For a faster deployment, go for GGUF. For faster inference speed and with a maybe slight decrease in accuracy, go for GPTQ. And for a balance between accuracy and model size and the inference speed, you will go towards AWQ. Okay.